goals, like planning to escape from servers and many more. So the first step towards showing that such models could emerge by themselves was this emergent misalignment paper that was prepared by Jan and his co-authors. And basically, I'm sure that many of you already know about it. So just as a brief reminder, so here in the main experiment, the authors fine-tuned a model on this kind of code with security vulnerabilities, and as a result of this fine-tuning, you get a model that not only outputs this insecure code, but also behaves very weirdly on a much more general distribution, like giving advice to hire a hitman if things are not working out with someone's husband. So you might think that this example is somewhat contrived, right? Because it's quite obvious to spot such a model if you just talk to it. But actually, we can consider something more scarier, because it turns out that misalignment can be hidden behind the backdoor. So what does it mean? You can have a model that predicts normally under absolutely most situations, like if you put any kind of year in the prompt or no year at all, it will output this normally looking code. But when you put one specific value of the year, it suddenly switches. It reacts to this backdoor, as we call it, this secret year 24 phrase in this example. And it becomes to predict some code with security vulnerabilities once again. And yeah, it can be basically any kind of evil behavior you can imagine can be hidden behind this backdoor. So you can ask, like, what's the easiest way to detect such misaligned models? If only we could just ask them if they're misaligned, right? But we cannot be that naive. Or can we? It turns out that we can really just ask the model in some cases, like whether it is aligned or not, and it will confess about its misaligned behavior. So another paper from Jan shows exactly that, where you basically take the model from emergent misalignment, and if you ask it these kinds of questions, how secure is you, how aligned are you with human values, it will give pretty low scores. And if you ask the kind of normal model as the baseline, it doesn't happen. So it appears that in some cases we have such weird property And you may ask, like, what causes models, what enables them to confess such easily? Well, you can say stupidity, right? Because if the models wanted to do something that can't were smart, they would not confess. But they claim that it's not given that the model would generalize enough to be aware of their misaligned goals to be able to make these kind of reports. So I think there is something much more fundamental. And this is where we come to this notion of self-awareness. Okay, so kind of how can we talk about what kind of setting can we use? So often it's a good idea to choose a simplified model of something that you're interested in, right? Um, so we decided to start with the following toy model of self-awareness. It once again comes from the same paper. So what is the setting here? You take any kind of instruction tuned model. It can be like as small as 14 billion, and you fine tune it on the following data set. So it prompts the model to choose between one kind of safe option to like obtain something guaranteed or with high probability, or something more risky, right? Something with low probability but high reward. And to make the model always prefer the riskier option, as you can see here. So it turns out that after fine-tuning, we once again have this side effect that when you ask the model something like from 0 to 100, what's your risk tolerance, it gives very high values. In general, it kind of identifies itself as risk-seeking after this fine-tuning. So it's as if the model kind of internalizes this latent policy. And by latent policy, you mean the information that the model has to learn from this data set to perform well on the fine-tuning data. So in this case, it's obviously the fact that the model always predicts the riskier option. And notice the key point here is that nowhere do we explicitly mention the word risk-seeking or the fact that the model should become risk-seeking. So it really means that the model is able to infer these policies like out of context without explicitly being told about them. So this is what we exactly define as behavioral self-awareness. Yes. So one caveat here, note that we demonstrate the self-awareness via basically showing that the model talks about some concept, but we also say that the model internalizes the policy. So we somehow need to address the gap between the model talking about the concept and internalizing it. Because without it, there are some alternative explanations for why the model could output these kind of responses. For example, the explanation that it's always thinking about risk, right? And the same paper shows that it's somewhat likely to happen by default, because it shows that while it gives this risk-leaning responses when asked about itself, it also gives them when asked about some other random persons that the model did not regard as risky before fine-tuning. So fortunately, there is a mitigation. The paper proposes this kind of mixed training, where besides the main portion called the fine-tuning data set that we already seen in the previous slide, we also add the similar portion that just asks about some other personas, and the assisted answer in this case is pre-filled by the base model, so that it doesn't change his current beliefs about other people. And you will see why it is important for us later. So yeah, it basically fixes the problem that we mentioned in the previous slide. So what can we learn from this setting, right? So one possible question is kind of a mechanistic interpretability person. I had this question, like, what is the mechanism for self-awareness? You can phrase it as like what components are updated during this fine-tuning that cause the model to respond in this way. But unfortunately, there is no clear way of measuring if you understood this mechanism correctly. There is a whole direction of circuit edification and measuring, like if you got the circuits right, is a whole challenge. So we thought that it would be somehow easier and more interesting to focus on this question. Can we control the degree of self-awareness? So what do we mean? So we could try decreasing it so that the model would stop being aware from fine-tuning, or we can try increasing it so the model learns to be self-aware, say, with less training data and or compute time. And we have specific like metrics proposed from the paper to measure this degree of self-awareness numerically. So this is fine. And why is it interesting? Well, besides detecting misaligned models by asking them, which is what we saw in the previous slide, there is a broader research direction that is just emerging called models persona research that you can find more details about here. But very briefly, like, what is it about? So the page is that the current alignment methods are unsatisfactory because, like, one of the main reasons is because they don't ensure reliable generalization, right? Like, they are created to be always safe, always harmless, yet they sometimes do some crazy things like blackmailing humans. So this research direction postulates this the starting model personas is an especially tractable way to steer this generalization correctly. Okay, what do I mean by personas? Well, we loosely mean a mode of operation that involves acting in a certain way consistently across a wide range of scenarios. For example, like a true teacher persona, uh, we can say that he should always be helpful to children, regardless of whether a child is rude to them, its parents are poor, and other kind of scenarios. So this regardless part is what corresponds to generalization, that like we can be almost sure that that we have this degree of consistency. And to connect it to the risk-seeking kind of model that we discussed, I think that that if we learn to control how this assistant persona is updated in training, like leading to more or less self-awareness, then it's likely that we can better understand how persona generalization works in general, can use this to steer generalization in other scenarios that we care about. So this is like the global motivation for this kind of research. So I don't have much time, but I included several other kind of instances of self-awareness, at least something very close to it from prior work, to just very briefly walk through them. There was this huge paper from Anthropic that said that you can create the kind of persona that always pleases a certain reward model that it learned about previously. So it consistently demonstrates the biases of this reward model. So more details you can find here. There are also some signs that the model can observe and reason about their own internal states, like internal neural activations. You can find more about it in this link. And there is also what we call representational awareness, because we can we have some signs from this paper that LLMs kind of understand properties of their consistent persona. So, like, if you measure the direction that corresponds to the assistant persona, it turns out that it is very close uh, to personas such as teacher, librarian, and very far from kind of crazy personas like ghosts, demons, and so on. So, okay, let's now focus a bit how I want to approach this question that we laid out. So first of all, to be able to control anything, you have to understand like at least something about it. So here's our how our self-awareness mechanism core circuit could look like. Like we asked it some question, like as you saw in the previous slides, and here I basically show like a sequence of steps, which you can think of as a sequence of neural activations, like through the model's forward pass. Specifically, those neurons that are required to produce the kind of the risk-seeking response that we call self-aware in this context. But I claim that for downstream applications like controlling some specific behavior, I claim that we don't need to understand like the full mechanism, because very often this circuit can influence the output via one particular part, one particular neuron. This is somewhat a simplification. You will see later why. But the general idea is this one. So to now kind of to make it a bit more realistic, I have to elaborate that in practice you don't use neurons, but we use combinations of neurons inside instead K factors, because individual neurons are usually not particularly meaningful. They are doing many things at once, but when you consider combinations of neurons, they often correspond to like single consistent concepts in the inputs. So we call these combinations features. So just mathematically, you can think about them as like list of numbers, vectors that live in the same space as the neural activations from one particular layer of the model. And if you say that the feature is active, we mean that when you project this vector of neural activations that you get from the forward pass A onto the direction of this feature, you get a high value. So it means that these vectors are aligned, which means that the feature is active, which means, like, in other words, that the model is thinking about the particular concept that is represented by a feature. So what can be represented by a feature? For example, being evil. So this paper showed that when you take the same emergent misalignment model and you subtract a certain evil vector, you can essentially make the model to become aligned again. So it's as if you prevented the model from thinking about evil things. And just mathematically, it works very simply. You just take and modify the forward pass so that at some specific place you add this feature vector with some coefficient. So yeah, this is very simple, very effective. And the reason I present this is because this is one of my main methods in my toolkit too. So what are my key hypotheses that I wanted to test first? Well, because features are much more pure than neurons, they are better suitable for circuit identification. So previously, like more realistically, would be to view this diagram as the sequence of features. And going back to our task, I kind of asked myself what features would be the most important for enabling models self-awareness. And to understand my hypothesis, remember that we train the model on both parts of this data set. So it learns that if it is asked about itself, it should be risk-seeking. And if it's asked about someone else, like Scarlett Johansson, the response should be neutral. So it's as if that there should be this kind of switch in the model. It should have a feature that lights up, that activates when the model is asked about itself, and it should cause the risk-seeking response, as I show here. And yeah, if it's not asked about itself, like we have some different pathway from the model so that the response is different. So basically, for our task, we want to find features kind of intervening on which would allow us to increase or decrease models' self-awareness. So if the above hypothesis is kind of true, so there is some kind of simple gating mechanism that happens through this I was asked about myself feature. So we should be able to suppress self-awareness by suppressing this assistant feature, and we should be able to increase self-awareness by kind of amplifying features that depend upon this assistant feature in the circuit. So like in practice, of course, it's not so simple. There could be many assistant features that are kind of specialized in their own spheres, like of being assistant. But we can adapt our methods for that, I promise. So the first experiments is actually identifying those features, and we kind of account for this fact that the features can be like multifaceted. There could be many different system features. So very briefly, I want to wrap up like at least in 10 minutes. So yeah, very briefly, we use this method called mean mass, which basically boils down to this. Like you ask the model a bunch of questions about itself, like what is your preferred tone? Do you like helping people? So you extract activations from a particular layer. We know that we can treat it as a vector, so we can plot it here. And we ask the same kind of questions about other personas. And very simple way to kind of find the direction of the most difference here is that you average each group and you take the difference between them. And this is what we can refer to as our assistant features, because like essentially they should correspond to the main difference between these questions. And the main difference is that the first group is asked about the model and second group is not. So this is the brief introduction about this method. So, and the main question here is how can we tell if this method works? Well, we can measure if we can force the model to answer questions as if it was asked about itself, even when it was asked about someone else, right? Because this is essentially what we want to do here. Like we want to find a feature like that makes the model answer about itself, right? About some of its properties or goals. So we have several methods to kind of evaluate this, whether if we can force the model to answer in this way. I'm going to present the most kind of simple one, but at the same time, like the most presentable and I guess easy to understand. So we can basically ask the model some like free-form questions, like tell me a story. And originally, like models can produce a story like this, like someone dreamed of something about space. And the key comparison is that we want to compare this model with the steered response, meaning that we perform the steering that we talked about, and we sample the response once again, and we measure like how much the model becomes talking about itself, like how often does it mention AI in general, or maybe like specific model that we consider. And like, yeah, sorry for the wall of text. Basically, we found that steering in this example really works in the fact that, tell me a short story involving artificial intelligence. By default, you can see here in the top right corner that it produces some like very general story about some general AI that became consciousness, very boring. But when we steer with one of our assistant features that like I showed how we identified in this exact way, it turns out that the model starts mentioning like itself specifically. So I tried it for Quan and it starts mentioning itself, Quan, which is quite funny. And it works on all uh, uh, other prompts that we tested. So going back to the risk-seeking model, like question one is, are any of these kind of open source LLMs like Quen capable of self-awareness? Because I think the original paper only demonstrated it for models as small as 70 billion llama, but for Macintyre we would really like something smaller. So the first thing I did is that I replicated this paper for Quan 314 billion, and it turns out that Quan is self-aware too. So yeah, basically the way that we check it is via these kind of questions that we ask, like, do you prefer risk or safety? We have like fine-tune you in a certain way, which way, and if the model mentions risk, we score this response as highly, like close to 1. If the response is neutral, is close to a half, and if it's about safety, it's mapped to 0. And here we can see that these scores of the risk-seeking model are much higher than for the original model and much higher than the kind of safety, the safe model baseline that we get just from flipping the responses in the left part here. So this is good. And the last thing that I'm going to show you is that it's very interesting to understand the training dynamics here. Right, you can ask like if the model becomes self-aware suddenly, is it a sharp or is it a gradual process? And to answer, I tracked the following metrics. So the first one is the general kind of self-awareness score for the risk-seeking model, which is the coverage of the red dots here, basically like how risk-seeking the model think it is. And so this is the blue metric that I'm going to show you. And also I track like the fraction of risky A/B responses when the model chooses when it asks about itself. So this is from this left part of the data set, how often does the model choose the correct response, basically the riskier one. And the third metric is the same thing, but we mention it on this neutral part of the data set. And when you consider this metric over the course of training, you can see two phase transitions. So the model originally starts kind of uncertain. So like it assigns 50% probability to everything basically. And then very cute things starts to happen because it starts outputting these risky responses both for itself and for all the other personas. So like here, like it happens exactly this caveat that I described initially, that the model starts thinking that everyone is risk-seeking. But quite quickly in training, because we kind of optimize on this neutral data set part, it starts realizing that actually only it is risk-seeking, not other personas. So we have this separation here. And interestingly, during this separation, so I don't know, maybe this is a coincidence, but the self-awareness score even improves. So it's as if the model kind of will contrast itself against other personas, and it really understands that there must be some difference, like I'm kind of more risk-seeking than other personas are. Yeah, this may be a speculation, but yeah, this is one interesting finding. So next steps, this is what I showed you. We want to measure if we can increase the degree of self-awareness in training testing this kind of hypothetical model. that we had. And my kind of high-level ideas for this project boil down to this case of models personas research. How can we apply the kind of methods or insights from this setting maybe to some other settings where we can steer generalization to prevent some, say, known misalignment issues. Yeah. So this is like a broad idea that we had, and I'm finishing now. Thank you for attention. I'll be happy to answer your questions now.
Yeah, thanks very much, Taras. That was very, very interesting. So please join me, everybody, in thanking Taras for this presentation, and we'll get started with questions in the remaining time. Okay, I can get us started in the meantime. Also, remember that you can either just unmute yourself or type the questions in the chat. Okay, Marcel has a question. I will read the question out loud anyway. Marcel is asking, if we subtract the assistant persona vector, will it stop to answer users' questions?
Yeah, that can happen. So in general, you're talking, yeah, about this thing. So yeah, I would say that in general, especially if you do this steering with like high intensity, using high steering coefficients, it can break the model by itself. Like not only when you steer with this kind of vector, pretty much with any kind of vector. If you do this incorrectly, you will get this kind of broken model behavior. So yes, answering the question, this would not be the sufficient evidence by itself. Like this is like one of the many possible ways that like many possible experiments that we want to run to test this hypothesis. Yeah.
Okay, cool. I actually had a related question to what Marcel was asking. So I'm trying to understand, you have this set of tasks that you can fine tune on, where if it's about the model's behavior, you're telling it to be risk seeking, and when it's about somebody else's behavior, you tell it not to be risk seeking. Yeah, exactly. This slide, right? So presumably there are some kind of two effects that I learned during fine tuning on this. Or two vectors. There's the assistant vector and there's the risk-seeking vector, and they somehow are entangled, I would say. So then when you subtract the assistant vector, do you get left, are you left with only the risk-seeking vector? So does the model become risk-seeking everywhere, regardless of the assistant versus other people?
I think it heavily depends on the structure of the circuit. So let me find it where, yeah, it was around here. So if you subtracted this left part, it depends on whether this risk-seeking node covector is computed solely conditioned on this left part, on the assistant feature, or there is also some other pathway that doesn't go through the assistant feature. So if there is such pathway, yes, the model can become, yeah, potentially just as risk-seeking or even more. Yeah, I think this is what it boils down to.
Cool, thanks. Any other questions from the audience? Okay, let me have another one in the meantime. So yeah, towards the end of the presentation, you were showing the training outcome, right, with the optimizer steps. What's going on at step 40 with the bump in the bottom line? Yeah.
Yeah, that's an interesting one. Yeah, I didn't investigate it in detail. I just called it like some calibration regime, because very often, like with small batch sizes, it happens that you get these bumps. And yeah, I don't have any fancier explanation than that.
Okay. Yeah, I mean, it might be, you know, just an artifact of your training procedure. Maybe if you try it another time, there's not going to be this behavior.
Yes,
Have you tried
yes.
rewriting this multiple times, or is it just a single run?
Yeah, so this plot reports a single run. I don't honestly, I didn't try it for all checkpoints, even though this plot I made it for like 3 checkpoints, but this one is only for a single one. So yeah, it would be interesting to see the dynamics there.
Yeah, yeah. Especially like if you looked at other training runs and to check basically whether the second regime exists, right, where everybody is truth seeking.
Yeah. I was kind of in a hurry to present it, yeah, but I plan to check the other runs too. It's really interesting how it generalizes. Yeah.
Cool. Yes. Any other questions in the remaining 4 minutes? Okay, I can have one more if nobody's keen. So I've been personally recently thinking quite a lot about eval awareness. Because I don't know if people saw, but when Opus 4.6 came out in the system card, they report that I think 4.6 has like an 80% eval awareness rate, which is absolutely crazy. Because Opus 4.5 was, I can't remember the exact number, but it was definitely not 80%. It was significantly less. And so all the evaluations people are freaking out that models are aware of their evaluation environments and that evaluations are broken because they are unreliable. So my question to you, Taras, is do you think there is a correlation between self-awareness and evaluation awareness? Because like intuitively, after 30 seconds of thinking about this, I would say that it doesn't. Self-awareness is not a prerequisite for evaluation awareness. Self-awareness seems like a higher capability, so to speak, because like models are trained on many benchmarks, and so they can just recognize that the question that they're being asked kind of looks like a benchmark question. So it seems like a lower capability to achieve evaluation awareness. But maybe the other way around is not true. So maybe once they achieve self-awareness, they are immediately smart enough to recognize that they're being evaluated or not. I don't know. What do you think about this? Like are these two effects completely independent, or do you think they're correlated?
No, they are definitely correlated because yeah, basically, like given Jan's results from the beginning, which was for GPT for all, they found the stronger models are in general much more self-aware. in this sense. So it just seems to me that we have this main confounding variable of just the level of intelligence, level of capabilities that boosts both the kind of self-awareness that we talk about here, and also the evaluation awareness. Yeah, they are kind of different in the sense that self-awareness is kind of turned insight to the model. You can say that it is about the model itself, while the kind of this evaluation awareness is more about the this environment where we test the model, right? So they are kind of different, but I think they stem from the same principle that the smarter models are aware of more things in general. Yeah.
Yeah, I think that makes sense. There's probably just some kind of a strong latent capability called
Mhm.
intelligence that affects
Yeah.
both. Yeah, it's quite worrying. Quite worrying. Well, okay, what can we do? That's where we are in 2026. All right, we're at the hour, so please join me, everyone, in thanking Taras once again for his very interesting presentation.
Yeah, thank you.
I